Okay, so we are back with our video lectures and we are jumping right back into 4.7, which is the area between curves. If you need to remind yourself of what we were doing before 4.7 and you don't quite remember everything, please feel free to check back on the weekly assignment guide. You can rewatch old lectures at like double speed or something, flip through the guided notes, flip through your notes, just kind of remind yourself of where we were at. And that being said, we're going to get into 4.7 now. And so our objectives are to evaluate the area between two curves. Nothing is due because we are on break, and your homework is the attached worksheet, area between two curves worksheet. Lecture will be linked when it is posted. So part one, the area between two curves. So first of all, recall that we can approximate the area under a curve between 2 points using a, think to yourself for a second, try to remember what we learned, and remember that approximating uses a Riemann sum, R-I-E-M-A-N-N sum. And we can find the exact area under a curve between 2 points using none other than, think to yourself, try to recall, a definite integral. Oh, I don't know why that happened. I-N-T-E-G-R-A-L, a definite integral. There's my favorite math mean ever, you versus the guy she told you not to worry about. Obviously the Riemann sums are less exact, and so yeah, anyway, that's my literal favorite math mean ever. Anyway, whenever we are finding the area under a curve using either of the above methods, we are finding the area bounded by the curve and the x-axis, right? The area under the curve and above the x-axis. Today, we are going to level up and we are going to find the area between two curves. The area between curves involves a particular region that is created from two separate intersecting functions. Geometrically, we can interpret the area as the area of our region equal to the area under function f minus the area under function g. This is especially obvious in a picture. This was supposed to be on the next page, I believe, because we're going to draw it out. So the area of the region between f and g. Well, first we're going to start out with a set of axes, and we're going to talk about between points A and B, which are generic points. They could be anything. So between A and B, we want to find the area between two curves. So let's say that we have function, so here are our bounds, and let's say that we have function f that is going to be blue and look like a sort of parabola. Oops, that's a little too big. Let's make that a little bit smaller. So we are going to have the area under f, here's function f, and we are going to have function g, which is going to be another parabola that looks like this. So we have function f and we have function g, and the area of the region between f and g, as it says underneath our picture, is going to be shaded in red, and that's going to be right here, right? Between f and g, we have that little kind of eye-shaped region, okay? And that is equal to, the area of the region between f and g is equal to the area of the region under f minus the area of the region under function g. And we're going to draw that again, right? So we have our axes, and we have our points A and B. And we are thinking about first the area under region F. So let's draw F and G on all of these again. So we have F, F, and G, G. And the area of the region between these two functions is equal to the area of the region under F. So the area of the region under function F is going to be this in blue, right? Under F and between F and the x-axis. And then subtracted by the area under function g. So the area under function g is going to be from function g to the x-axis. And we can see in this picture now that if we subtract the blue region and the green region, we get our red region. So the area of the region between our two functions is the area under f minus the area under g. And we can write that statement using none other than calculus, right? So the area is equal to the integral from A to B. Those are our bounds. We're talking about the area from A to B of f of x minus g of x dx, right? That's equal to the area or the integral from A to B of f of x dx, which is the area under region F. So this integral right here corresponds to this graph, minus the integral from A to B of g of x dx. And that integral corresponds to that picture right there. So hopefully take a second, think about this, and understand how the area of F minus the area of G gives us the region that we want, which is that, again, that red highlighted area. Okay. Once we have determined which region we are working with, we find the area by dividing the area into vertical rectangles. The height of the rectangles is going to be the value of the top function minus the value of the bottom function. The width of the rectangles is dx. So this is, again, this whole part right here is just getting at the fact that we are finding the area by using a definite integral, which again comes from Riemann sums. And then in order to sum up the area of all of our rectangles, we integrate, okay? So take a second, pause the video, think about this, and we are going to jump right on into a good old example problem. So, for instance, find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So, first things first, we want to graph this out. So I'm going to draw my axes right here and find the area of the region bounded by the graphs of, first of all, we have y equals x squared plus 2. I'm going to make that guy yellow. X squared plus 2 is going to be a parabola shifted up 2. So that's going to be right here. Oh, that's not shifted up enough. I'm going to actually go ahead and put that up even more. Right about there. Y equals negative x. That is going to be a nice line that goes like so. Y equals negative x. X equals 0. That is going to be my axis. These x equals 0 and x equal 1. Those are going to be my bounds, right? Because x equals 0, we know is going to be a line right here. X equals x equals 0. And then x equals 1 is going to be over 1 right about here. X equals 1. Okay, and so now we can see the region between our two curves is going to be right here. And that is not just the area under y equals x squared plus 2, because we are going below the x-axis now, okay? So area is that red that we want to find. Area is equal to the integral from, our bounds are 0 to 1, because that is what bounds the area we want to find, our shaded area that we see in our picture, of f of x, which is x squared plus 2 dx, minus the area under the curve of our other function, which is still going to be from 0 to 1, and our g of x is negative x dx, okay? So now we can go ahead and evaluate these integrals. The integral of x squared plus 2 is going to be x cubed over 3 plus 2x from 0 to 1, and that is going to be, we could remove this minus and turn that into a plus, and then the integral of x is going to be x squared over 2 from 0 to 1. We can go ahead and plug in our upper bound and our lower bound, and in the first bracket you should get 7/3, and in the second one you should get plus 1/2. 7/3 plus 1/2 is equal to 17/6. So the area between our two curves here is 17/6. So as you can see, once you have a clear picture, these problems aren't especially difficult. Okay, so beautiful. Number 2, find the area of the region bounded by the graphs of y equals 2 minus x squared and g of x equals x. I don't know why I didn't give any space for this one. So let's do this problem. Find the area of the region. Okay, so again, we want to start with our axes right here, nice and clean. And now we want to draw our functions. First of all, I have y equals 2 minus x squared. And so, oh, where'd my other axie go? Oh, that's weird. Okay, so we have y equals 2 minus x squared. That's going to be an upside down parabola like so. So that's going to be my green function. And g of x equals x is going to be just the most basic function that goes like so. Okay, and now I can see that I wasn't given bounds, but that these two functions are kind of self-bounded, right? I have this red area right here that is my region, but again, in order to find the area of that region, I need bounds. So I need to know what point is this, 1, and what point is this, 2. And actually, even though I'm not given that information, I can find that information by setting my two functions equal to each other. So I'm going to have x is equal to 2 minus x squared. I'm going to move everything to one side. So I'm going to have x squared plus x minus 2 equals 0. I'm going to factor that bad boy. X minus 1 times x plus 2 equals 0. Therefore, x is equal to 1 and x is equal to -2. Okay, so I know that this point over here is going to have an x value of 1 and then something you could figure out by plugging it into the function, but you really only need the x values for bounds. This point is actually 1, 1. And then down here, you are going to have the x value -2, and then plug that into a function to find your y value, which is going to be -2, -2. And now we can go about finding our area. So area is equal to the integral from -2 to 1, which we now know are our bounds, thanks to a little bit of algebra work, of our top function, which is 2 minus x squared dx. Oh my gosh, 2 minus x squared dx minus the integral from -2 to 1 of our bottom function, which is x dx. I want you guys to go ahead and try to evaluate these on your own, but the ultimate answer that you should get should be 9/2. And we can go through the work on that if we need to in class, but again, at this point, you should be pretty comfortable with evaluating definite integrals, and so you shouldn't have too much of a problem with this. If you get the wrong answer, it might be because of your algebra, so double check that, but again, we can do it in class if needed. All right, beautiful. Scrolling on down. As you might have noticed, since our integrals both have the same variable of integration and bounds, we can consolidate them into one integral. This means that the area between two curves can be written as the area from A to B of top minus bottom dx. So if we actually go back to this previous example that we just did, we could rewrite area as area is equal to the integral from -2 to 1 of 2 minus x squared, which is our top function, minus our bottom function, which is x minus x dx. And if you evaluate that bad boy, you should also get 9/2. So same answer, you can actually consolidate area between two curves and make it nice and easy for yourself in one single integral. So it's kind of like 2 for the price of 1 or something. All right. Part 2, special cases. In some cases, the regions are formed by curves that intersect at more than 2 points. In such cases, we may need to use more than one integral to determine the area between the curves. For instance, let's think about the regions formed by the graphs of y equals -x squared plus 3x, which is the solid line, and y equals 2x cubed minus x squared minus 5x, which is the dashed line. First of all, we want to shade the regions that are formed. So first region, I'm going to shade in red right there. And second region, I'm going to shade in green right there. So to find the area between these two curves, we actually are going to need to find the area of two separate regions. So area of region 1, that was my red region, is going to be the integral from A to B of top minus bottom. First thing I need to do here is find my points of intersection, right? So in order to do that, I'm going to set my two functions equal to each other. So I am going to have -x squared plus 3x equals 2x cubed minus x squared minus 5x. I'm going to add x squared minus 3x plus x squared minus 3x. 0 is equal to 2x cubed minus 8x. Then I can factor out 2x, so I have 0 equals 2x times x squared minus 4. 2x equals 0, so x equals 0. X squared minus 4 equals 0, so x equals plus or minus 2. So this x-intercept is going to be -2, this one is going to be 0, and this one's going to be +2. So those are how I find my bounds. And now let's find the area of the regions. So region 1 is going to be the integral from a to b, which is the integral from -2 to 0 of top minus bottom. So my top function is dashed in this case, which is in fact the function 2x cubed minus x squared minus 5x minus bottom. My bottom function is the solid line, which is -x squared plus 3x dx. So I'm going to have to distribute that minus, and then you should end up with this definite integral equaling 8. Again, we can go through this in class time if you get tripped up somewhere in the calculus of evaluating a definite integral. And then the area of region 2 is going to be the integral from a to b. Our a is now 0 and our b is now 2. Of top, our top function is now -x squared plus 3x minus bottom, which is 2x cubed minus x squared minus 5x in terms of x. So we do that dx. Remember to distribute this negative, and for this integral, you should get 8. So then the area of the region we can find by adding the two integrals together, and that is going to be 8 plus 8 equals 16. Okay. Okay, so there's another example here. I want you guys to go ahead and pause the video and try to figure out this one on your own. I should really recommend using Desmos to look at the graphs, or your graphing calculator to look at what these two functions actually look like. So you can very definitely see the two regions, and then remember to find those x values that you need for your bounds, set the two functions equal to each other, and solve for x. And then again, write out your definite integrals, top minus bottom, find the area of the two regions, and add them together. And for this problem, you should get 1,136 over 3. So that is the final answer for that guy. And we will go over this one in class. All right, part 3, and that brings us to the very end, which is part 3, horizontal rectangles. Sometimes, instead of using multiple integrals with respect to x, we can find the area between two curves using horizontal rectangles and evaluating our integral with respect to y. So integrating with respect to y, we follow the exact same rules that we do with respect to x, except for we need to make sure that the variable in all of our equations is y instead of x. Okay, so vertical rectangles area is integral from a to b of top minus bottom. Dx horizontal is going to be y1 to y2. So we're going to we are going to have to use y points on the y-axis of right minus left dy. So for instance, given the diagram below, use horizontal rectangles to find the area of the region between x equals 1/2 y squared minus 3, which is our solid line, and y equals x minus 1, which is our dotted line right there. So again, we need these y values. So what we are going to do is we are going to set our two functions equal to each other. So I'm going to have, well, first I know that I have x equals 1/2 y squared minus 3 and y equals x minus 1. I want to solve for y, so I'm going to solve y equals x minus 1 in terms of x. So I know that this is equal to, add 1, x equals y plus 1. So now I have y plus 1 equals 1/2 y squared minus 3. I can go ahead and subtract y, subtract 1, minus y minus 1. I don't know why my screen got all weird for a second there. Oh, I guess it didn't. So then I get 0 equals 1/2 y squared minus y minus 4. I don't want to deal with that 1/2 fraction, so I'm going to multiply everything by 2, and then this becomes 0 equal to y squared minus 2y minus 8. I can go ahead and factor that bad boy, and I will get 0 equals y minus 4 times y plus 2. So y is equal to 4 and y is equal to negative 2. So this down here, y equals negative 2, y equals 4. And now that I have my y values, I can write the area between these two curves using horizontal rectangles, which go this way instead of vertical rectangles. And remember, we are summing these rectangles using a definite integral. So I'm going to write this integral as the integral from -2 to 4 of my right function, which is y plus 1, minus my left function, which is 1/2 y squared minus 3 dy. And so go ahead and evaluate that integral, and you should get 18. This equals 18. All right. And then if you scroll down, there is one more example that we have. I don't know where my little Apple Pencil thing went. Oh, here it is. There is one more example that we have, so you guys can go ahead and try that one on your own. The final answer should be 9/2 for this guy. Again, do the same thing that we just did above, find those y points and evaluate your definite integral from right to left, or right minus left. And we can go over this guy in class as well. Other than that, that is all I have for you. Homework is posted. And if you have any questions, as usual, please feel free to reach out or come to tutorial. And that's all I got for you guys today. Thanks. Have a lovely day.